In this lecture, I will explain how to perform optimal spatial resource allocation in cellular networks. So that is about how you optimize the beamforming in a multi-user MIMO system. And it's all based on a book that I wrote together with Edward Jortvik. It's called Optimal Resource Allocation in Coordinated Multicell Systems. And you can download the free PDF and simulation code online. You find the links in the description. So the outline of this lecture is the following. First, I will explain a little bit about what cellular networks is, what is a system model we will be using, and what are the different performance metrics that matters in this context. Then we will formulate our problem in the most general form and define what resource allocation really means. And it will turn out to be a multi-objective optimization problem. And then in order to solve it properly, we need to make a subjective resource allocation decision and define something that we call a utility function. We will look at how the choice is affecting our computational complexity. And finally provide some structural insights into how the beamforming is actually geometrically structured. Starting with introduction, what we are considering a bit vaguely is that we would like to transfer information to users in a network with multiple base stations and multiple user devices. And we would like to divide resources between them, which is time, frequency, and space, and particularly it will be the spatial dimensions that we will be focusing on. And this is a downlink coordinated multicell systems, so we have many transmitting base stations. These are the base stations illustrated here. We have many receiving users, and it's a so-called multiple input, multiple output system, or MIMO, because we have multiple transmit antennas at multiple locations and multiple receiving users. And the main thing here is that they're all sharing the same frequency band, which means that all the transmitted signals reaches all of the users, but to different extents. And the limiting factor will then be the inter-user interference that we need to control. The traditional way of dealing with inter-user interference is to avoid it or suppress it to a larger extent. And this results in some kind of orthogonal transmissions within each cell. There are concepts like TDMA that was used in 2G, for example, where you are sending to different users at different times, so time division multiple access, or OFDMA that was used in 4G, where you are transmitting to different users at different frequencies. However, with multiple antenna transmissions, we can do things differently. There is the concept of beamforming that allows you to transmit signals in different directions towards different users. And then you can transmit one signal to user 1 and another signal to user 2 at the same time. And this should be contrasted against only having one antenna. When you're transmitting one signal, it is spreading out in all directions, and therefore there is no point in trying to transmit to multiple users at the same time, because you will always get a mix between the two signals. So this is the main difference from classical resource allocation. When you have multiple antennas at the base stations, we can serve multiple users at the same time at the same frequency, and this is known as spatial division multiple access, or SDMA, or multi-user MIMO. Designing the multi-antenna transmission can be a challenge on its own. We need to know something about the channel to the user, and then we can point the beam, and this is called beamforming or precoding. And even if we're focusing towards a particular user, there will be signal leaking in many different directions. So if there's another user in a particular direction, there is a big risk that some of the signal will hit that user as well. And when we are designing a beam towards that user, say the red one here, well, then there will be some part of its signal that is leaking towards the original user. So this is creating the beamforming design problem, which is easy for one user because you just want to point the beam towards that user to give it the maximum amount of power. But it's difficult when you have multiple users because of the interference that we are creating between the users and would like to control. This is a challenge already in a single cell case with one transmitter with multiple antennas. And if you want to go from a single cell to multiple cells, well, the naive multicell extension would be to divide the base stations to different clusters, and then you do some kind of SDMA transmission within each cluster to serve the different users there, and then you make sure that there is no interference between the clusters by, for example, orthogonalize them, use different frequencies and other traditional methods. But This is not what we want to do in real systems because we would like to use all the frequencies all the time in all the cells. And therefore, a coordinated multi-cell transmission is what we are opting for. This is some kind of SDMA in a multi-cell scenario where the base stations are cooperating in order to deal with interference, with beamforming, and use all the frequencies everywhere. This technology has been given different names over the years, things like multi-cell processing, coordinated multipoint or COMP, network MIMO, cell-free massive MIMO, more recently distributed MIMO, and it's all about viewing the entire system as just one supercell with base station antennas spread out but operating as if it were one cell. But it is still quite different because you have different data knowledge at different base stations, you have different channel knowledge, and you might have different power constraints at a different base station when you are designing your downlink transmission. So what we are looking for is some kind of general multi-cell coordination methods here, and we would like to keep in mind that adjacent base stations might be coordinating the interference that they cause into each other to limit that to a large extent through beamforming. And some of the users might be served by multiple base stations. We can capture this in a very general way using the concept of dynamic cooperation clusters. Around each base station, there is an inner circle containing a number of users. We call it D1 here, which are the users that this base station is sending data to. Then there is an outer circle, a bigger area, where we have some users, including the ones that we are sending data to, but also some additional ones where we like to suppress interference that we are causing to them. So we call this C1, or DK and CK for base station K. And outside both of these circles, we expect that the users are that far away will not be caused by much interference. We can ignore them, and it would anyway be impractical to try to get any knowledge about their channels and coordinate the decisions over really big regions. With this model, some users, like the one circled in red here, can be in the inner circle of multiple base stations. You see it's in the blue circle of both base station 1 and base station 2. So this user will get data transmitted from both of these base stations. Then there are some users that are in the inner circle of one base station. This one is in the inner circle of base station 1 and in the outer circle of base station 2. So it will receive its data from base station 1, but both the base station will avoid causing interference to the user. And some users can be very far away so that they are only affected by one of these base stations. So here is one user only affected by base station 2, and one user that only base station 2 is caring about the interference, but not base station 1 at all. The dynamic cooperation cluster concept was first introduced in our paper in the transactional signal processing in 2011. And it is a very general concept that can encapsulate a lot of different scenarios. One example is an ideal joint transmission scenario where the entire network is just like one cell, so all the base station serves all the users. That means that all the users from 1 to KR, which is the number of users here, is in the inner circle where you're sending data to all the users, and also in the outer circles of all the base stations. Another example is the so-called Wiener model, which is an abstraction in information theory, where the user receives signals from its own and the two neighboring base stations in the one-dimensional case I'm illustrating here. It could also be a two-dimensional case where all of the surrounding base station is only the one that reaches you. In this case, you will receive data from your own base station, D1, and the outer circle will also encapsulate the users in between you and the base stations next to you. And you can define this with joint transmission or coordination between the cells in a very different way. There is also the concept of coordinated beamforming, where each base station have their own unique set of users. So we see the inner circle is non-overlapping between the different base stations, but all the users are in the outer circles of all the base stations, so we have interference coordination across all the cells. A special case of this is known as the interference channel in information theory, where every base station is only serving one user. You can have some kind of heterogeneous network where you have a macro base station that is serving a lot of users in a big area, and it has all of those users within its inner and outer circle. But within its coverage area, there's also some small base stations being deployed, and they have their inner circle with some users that they are individually serving. They might also be jointly served together with the macro base station. They have some outer circle of an area where they cause interference. It is smaller because they use less power. And we can have some interference coordination and joint transmission between both the macro and the small cells. You can also use dynamic operation clusters to model a cognitive radio system, where you have a primary system that is using the spectrum for something, communication or something else, and then you are considering a secondary system that is borrowing the spectrum, and it's using it to do data transmission to some users here, which is in their base station's inner cells. And then there are some outer area, which also includes the primary system, where you like to coordinate your interference and make sure that you cause so little interference to the primary system that you are not destroying its operation. That is the essence of cognitive radio. And in our textbook, Optimal Resource Allocation in Coordinated Multicell Systems, we have also some other examples. Spectrum sharing between operators, physical layer security, and you can make up many other kind of scenarios where you can use the dynamic operation cluster to model all of these different systems at once. We are now ready to start to define what resource allocation really means. And it's a little bit imprecise, but we would like to select our beamforming transmission to maximize some kind of system utility, the performance of our system. And this means allocating power to the users in different spatial dimensions, how we are transmitting towards them. And we should satisfy some constraints, which could be physical, regulatory, or economical. And some of the assumptions that we will be doing in this lecture is that we are doing a linear transmission and reception, so we do classical beamforming. We have some perfect synchronization whenever needed between our transmitters. We have flat fading channels, which could be that we are studying one subcarrier in an OFDM system. We also assume that we have perfect channel knowledge everywhere, ideal transceiver hardware, and with that we can optimize everything in a centralized manner. And these are all things that we are relaxing in our book if you would like to know more about that. It is now time to define our system model mathematically. We have KT transmitting base stations with multiple antennas each. We have KR receiving users across our entire area. And we have a channel vector, HK, from that user K to all of the base stations. That means that we can take this vector and cut it up into different pieces, in particular KT different pieces, each of them assigned to one of the base stations. And we have NJ antennas at jth base station, so the part here, HJK, from base station J to that user K, has a dimension which is equal to NJ. And in total we have N antennas, which is summation over all of the antennas for different base stations, and that means that N is the length or dimension of the vector HK. The downlink transmission happens as follows. We are transmitting a signal S1 to user 1 and SKR to user KR. And these are the one-dimensional intended information signals that is encoding data to different users. Then we need to transmit them from our different antennas. And for user 1, we create a beamforming vector V1. We multiply them with D1, which describes the inner circle of all of the different base stations. And we will come back to how we define that. And then we are doing the same thing for all the different users. They have their beamforming vectors multiplied with a matrix that describes the inner circle, namely who is transmitting to that user. We take this vector and multiply it with our information symbol. We add it up, and then the signal is transmitted over there to the different users. For user 1, we have its channel vector. We have C1, which is a matrix describing which of the different base stations can actually reach this user, namely have this user in their outer circles. And then we add noise in the receiver hardware, and that can also contain some small amount of interference that comes from the outer parts of the area that is not in the outer circle of any of the different base stations. And finally, we have some received signal, Y1 at user 1. And this goes on for all of the different users in the same structure. So we have one system model for all of the different multi-cell scenarios, which means that we can do our optimization for all of these different system models at the same time. I haven't described how the CK and DK matrices are defined, so let me give you an example for a coordinated beamforming scenario. So we consider one user here, that user is in the inner circle of base station 1, but not of any of the other base stations. Then its decay matrix is a block diagonal matrix containing an identity matrix for the blocks where the base stations are serving this user by sending data. So it's only the first block, and zeros for the other ones. And then all of the base stations are considering this user when it comes to causing interference. So therefore all the base stations coordinate the interference, and we have a CK matrix which is block diagonal, and each block is an identity matrix because we are considering the interference there. So we are really switching between identity matrix and zero matrices depending on if you're in the inner circle or not when it comes to decay, and for CK if you are in the outer circles or not. Alright. We also need to define some kind of power constraints which limits the radiated power according to some regulations, protect the dynamic range of power amplifiers, maybe manage the cost and energy expenditure in our network, and control interference to certain uses, such as in a cognitive radio scenario. And we would like to do not one of these things but all of them at the same time. And in general we might have L power constraints. Each of them is such that we are making a summation over all of our different users. We take their beamforming vectors, we multiply them with some kind of weighting matrix, which is a positive semi-definite matrix, multiply with VK on the other side with a conjugate transpose. So we have a quadratic form here, and then we want this to be smaller than some positive limit. So what could this really entail? Well, for this general structure, we can, for example, model a total power constraint. In that case, we only need one constraint of this kind. And we have a weight matrix here, which is just an identity matrix. So we take each vector and multiply with itself. That is the squared norm of that vector. And then the Q here, Q1, will be the maximal total power from all our base stations. We could also have per antenna constraints everywhere in our entire network. In that case, we have n antennas. So we have n constraints. For each of them, we have a weighting matrix here, which is a diagonal matrix with a 1 on only one entry and zeros elsewhere. And we create all such possible matrices. And then we have a maximal power for the Lth antenna in the Lth constraint. So with this general form, there are many different constraints that could be defined. Finally, we need to figure out how do we measure user performance in a system like this. And one can come up with many different metrics. One of them is the mean squared error, which is a difference between the transmitted and the received signal after we have processed the received signal. And it's fairly easy to analyze because it typically becomes a quadratic form, but it's quite far from the actual user perspective because they will not know what a particular mean squared error value means. Is it good or is it bad? Alternatively, you can consider the bit or symbol error ratio, which is a probability of error for a given data rate. And it's kind of intuitive to interpret what that means, but it also leads to either complicated expression when you have channel codes, or you have to ignore channel codes, and then you don't have a particularly practical metric. A third option will be the information rate, which is the bits per channel use, or bits per second in hertz. And that comes from mutual information, which means that you need to assume a perfect and decoding and very long channel codes. On the other hand, it might still be closer to reality because we are sending a lot of data in practice. But the good thing is that we don't really need to care about what metric we are choosing, because all of these ones are improving when we improve the signal to interference and noise ratio. The signal power divided with the interference power plus the noise power. So we can optimize that one instead. So a generic model also for the performance metric might be that we have any function of this SINR. Let's call the function GK for user K. And we have an SINR expression for our case that looks like this. So here we have our beamforming vector, here we have our channel to the user of interest, user K, and we have the D and CK matrices inside of it. We have the noise variance for this user, and we have the interference, the signals transmitted to all of the other users. And we have their beamforming vectors, we have the channel to the user of interest, and we have the D and CK matrices inside of this as well. And the only thing we need to assume is that GK is an increasing continuous function, and for simplicity that if the SINR is 0, well then the performance is 0 as well. these are the only thing we need to assume in order to establish an optimization framework. An example of such a function is the information rate, where gk of SINR is log to a 1 plus the SINR. And you can define similar functions for all of the other metrics that I was describing. The difficult thing here is not the function gk, but how the SINR depends on all of the beamforming vectors, v1 and vk, because vk is appearing in the numerator and vi in the denominator in this scenario. But we are finally ready to define our problems that we will actually be solving in a mathematical way. So we would like to maximize the performance of user 1, g1 of SINR1, and the performance of user 2, and so on up to user kr. And we would like to do it by selecting our beamforming vectors subject to our L power constraints. And since we not have one metric, but kr different metrics, this is a multi-objective optimization problem, which is generally impossible to solve in the sense of maximizing the performance for everyone at the same time. We must make decisions on how to divide the power and how to cause interference between the users, and in that way limit other users' performance. We can study this trade-off in terms of the performance region, which is the feasible points of performance for different users that we can achieve at the same time. For example, for some particular selection of v1 to vkr under our power constraints. So it might look like this for two different users, user 1 here and user 2 here. The blue area is all of the different performance points that we can achieve at the same time. So there's certainly a trade-off between them. And there are different names here, rate region, capacity region, MSE region, and so on, depending on what kind of metric we're actually using. But let's just call it performance region. And the part here of interest is the outer boundary, known as the Pareto boundary, where we cannot improve for any of the users without degrading for the other one. So if we have a performance here of user 1 and we like to improve it upwards here, we need to decrease the performance for user 2 in order to still stay within the performance region. So over here we are caring about user 1 only. Up here we are caring about user 2. And somewhere here in between we are balancing between the performance of the two different users. Can this region just have any shape? Can it look like this with a hole here and a tooth here and whatever? This looks like a man. Well, no. One can prove quite easily that this needs to be a compact set and so-called normal set, which means that if one point is inside the region, you should be able to degrade the performance and still stay within the regions. We can't have these strange shapes over here. Everything in a box like this needs to be included. But there are many different possible shapes. So here is a case where our region is square-shaped. In this case, the Pareto boundary is only at one point, because we can actually, in this extreme case, give both of the users the maximum performance at the same time. We can have this kind of shape here, which is a convex and normal region. We can have a non-convex and normal region looking like this. And we can have a concave and normal region looking like this. All of these are possible. So depending on the shape, if it is convex, then there is a weak interference between the users, so we can achieve quite a lot of the performance for one user without degrading much for the other one. When it's concave, well, we have a strong trade-off where a small improvement for one user causes a large degradation for the other user. One can consider some kind of scheduling where we are time sharing between strongly coupled users, and in that way we can actually make any region like this convex by saying part of the time we are here, part of the time we operate here, and if we are splitting the time equally between them, we will actually operate here on the average, which is somewhere in between and outside this region. So one can potentially claim that this region should always be convex. However, in general, it's really hard to know how this region looks like, so it's not easy to do something like that. So we have very many different Pareto optimal points, but which one should we choose? We have the single user points, and if we are drawing a line from both of them, we can create this utopia point where both of the users are getting their maximum performance at the same time. But unless it is inside the region, we need to make a trade-off. We can consider the utilitarian point where we like to make the sum performance as big as possible. Or we can have the egalitarian point where we try to maximize the fairness to make sure that both of the users get the same performance. and these are typically not the same thing. And there's actually no objective answer here when the utopia point is outside the region. Only subjective answers exist, so we need to make a own opinion about what we would like to achieve with our system. This leads us into the area of subjective resource allocation, where we as system designers need to select a utility function that takes as input one point that might be in our performance region and is assigning a number that tells us how preferable that point is. A larger number means better, so it should be an increasing and continuous function as well. And some examples of this might be that we take the sum performance, so we just sum up the performance of different users. We can have some kind of proportional fairness, where we are multiplying together the performance of different users. We can also view this as the geometric mean, so we are taking the kr root of this, and you will have the actual geometric mean. We can have the harmonic mean, looking like this, or we can have some kind of maximum fairness where the important thing is that we are maximizing the minimum performance of all the different users. And we can probably put this on a range between caring only about aggregate performance but not who is getting the performance, and caring only about user fairness, making sure that everyone gets the same performance no matter what performance it is. And we can of course change all of these different functions as well and add some weights to move in between these different extremes. The concept of selecting a utility function to handle a multi-objective optimization problem is known as the a priori approach, because we are selecting utility function before we even start trying to do any optimization at all. And in this way, we are creating now a single objective optimization problem because we would like to select our beamforming vectors to maximize our utility function. So G here is the performance of the different users, subject to our power constraints. And this is a starting point of a lot of papers that you might have read, where you already have a selection of this utility function from the beginning, even if it is inherently subjective and actually also affects the solvability of our problem. And the point I want to make here is that you should always have a motivation in mind when you're formulating a problem like this, because you have already injected some subjectivity when you selected your utility function. So think about that when you're choosing to solve a optimization problem in wireless. And I think the pragmatic approach is to try to select our utility function in order to enable efficient optimization, so that we can get a low computational complexity. So let's have a look at different kinds of optimization problems that we might come across. We have the linear problems, which have the lowest computational complexity among the things that we could imagine getting here. We then have a bigger set of convex problems that are also efficiently solvable. You can extend this into quasi-convex problems, where you can solve it as an iteration of convex problems and still find the global optimum. Then we have the monotonic optimization problems, which you can solve to global optimality, but it requires exponentially amount of time. And finally, you have all kinds of weird optimization problems that you might not even be able to solve in any reasonable amount of time. So there are three main classes of optimization problems. The convex ones have polynomial time solutions, which makes them practically solvable. We have the monotonic problems, which have exponential time solutions. So we typically need to do approximation in practice in order to solve such problems. And then we have the arbitrary problems, which we can't even solve unless we are making approximations. We will now classify three important problems and determine their complexities. One thing that I call the easy problem, which is a starting point for a lot of other solutions, the weighted maximum fairness problem, and the weighted sum performance problem. And we will see that they have very different complexities. So the first example is the easy problem, which means that we are given one performance value that we would like every user to have, G1 to GKR with a tilde here. And the problem is to find one beamforming solution that attains this point and minimize the total power while doing that. And this turns out to be a second order cone or semi-infinite program. And you can find the global solution in polynomial time. You can even use some implementations such as CVX or JALMIP to find it. And alternatively, you can do some fixed point iterations and use something known as uplink downlink duality to find the solution very effectively. And there is a wide range of different algorithms developed over time, which is handling total power constraints or per antenna power constraints or the general constraints that we are considering in this video. So this problem is something that we can solve and figure out if it is solvable or not under our power constraints. So let's now consider problem 2, maximum fairness. And we would like to classify this problem where we maximize the minimum of the performance of every user with some weights, wk, which are fixed, and we should select our beamforming vectors subject to our power constraints. Since we are maximizing the minimum of wk, gk, then there is no reason for a user to have a larger value than the other ones, meaning that wk and gk will be the same for all of the users at the optimal location. Let's now consider the performance region here for 2 users. All of the points where wk, gk is the same will be on this line here, pointing in the vector direction w1 to wkr. And some of the points are inside the region, some of the points are outside the region, and the solution to this problem is to find the point that is crossing the Pareto boundary. So this is the optimal solution. So how can we now figure out what that point is if we are not knowing the performance region? Well, we can generate an algorithm based on what is known as the bisection. We start by considering the line segment from the origin up to some point that we can be sure is outside our performance region. It could, for example, be based on the utopia point. And then we consider the point in the middle. That is just one point, and we would like to know, is this point inside or outside the region without actually knowing how the region looks like. And figuring out that is the same thing as solving the easy problem and see if it is feasible or not. In this case, it is feasible, and that will tell us that all the points that are lower on this line than the midpoint is also achievable, so we can remove those ones. And now we have a smaller line segment. We consider the point in the middle of that one. When we solve the easy problem, which we can do in polynomial time, well, then we will figure out that the problem is actually not feasible because we will need more power than our power constraint is allowing for. So therefore, all the points that are further out can also be removed, and we have a shorter segment. And we continue like this. This point is inside the region, so we can take away everything that is further down. The next point is outside the region, so we remove this thing, and very quickly we converge a very small interval which is around the true optimal point. So what we have designed now is an iterative algorithm where every subproblem is a convex optimization problem, the easy problem. And this iterative procedure is very efficient. It's a line search procedure with linear convergence, and it's going to be a one-dimensional problems independently of how many users we're having, because we're always searching along a line in 2 dimensions or 3 dimensions or 4 dimensions and so on. So this is an efficiently solvable problem known as the bisection algorithm. In terms of classification, this is a quasi-convex problem which belongs to the convex class in a sense, because we are solving a sequence of convex problems to solve it. It has polynomial complexity in number of users, number of antennas, number of power constraints, and it might be feasible to solve something like this in practice. There is a long history of solving such problems, from some early works to some main references to cases where I've also been working on channel uncertainty when solving problems like this. Let's now consider the third kind of problems, the weighted sum performance. Now we would like to maximize the sum of the performance of different users with some different weights here. And when we have solved this problem, we will have a certain value here. And if we are considering 2 users, then the weight for user 1 times its performance plus the weight of user 2 times its performance will be equal to that optimal value. And you might recognize this as the equation of the line. It's a line that goes like this. It is crossing the region in only one point. And that is the optimal operating point. The issue that we will be facing is that this optimal value is not known beforehand. So we would have to solve the problem to figure it out. So should we be on this line or that line? And when we are considering different lines, we need to consider every point on that line in order to figure out where we are crossing the region. So the distance to the origin is unknown, and when we are going from 2 users up to more users, this line will turn into a hyperplane with a dimension which is equal to the number of users minus 1. So more and more users gives us more and more complexity. So this is clearly harder to solve than the maximum fairness problem. It is actually a non-convex problem. So the weighted sum performance problem is non-convex even if the power constraints are convex. So the reason is that the utility function is a monotonically increasing metric in the beamforming vector of the user of interest and decreasing in all of the other users. And it actually is belonging to the category of monotonic optimization problems. Could there be some efficient magical algorithm that solves these kind of problems efficiently? No, it's actually provably in NP-hard problems, non-deterministic polynomial time hard, and this is proved in papers like this. And that means that we know that there are no efficient algorithms. But even if the complexity is exponential, it might only be exponential in some of the parameters. We have parameters such as number of users, number of antennas, or the number of constraints. Are monotonic problems impossible to solve? No. We can actually devise algorithms based on monotonic optimization theory. And it is based on trying to bound the optimal value from below and from above, and iteratively improve the maximum and the minimum value until the difference between them is smaller than epsilon, some parameter that we are setting from the beginning. And what I will show you is an algorithm where we essentially are solving weighted maximum fairness problems in order to improve on Fmax and Fmin. The solution methodology is known as monotonic optimization, and there is a great introduction to this topic by Tui. And there are algorithms such as the polyblock algorithm and the BRB algorithm. I will show you this BRB algorithm, which stands for branch, reduce, and bound. And you are guaranteed to get a global convergence. You will find the solution to any accuracy epsilon in finitely many iterations. But the time is actually exponential, but only in the number of users. It's polynomial in the number of antennas and number of constraints. So I will give you an example here of how it works. You have a Pareto boundary here and your achievable region, and you have your maximum sum rate point that you want to find here. You just don't know the region and that value. But you are creating a box here. The way that this iterative algorithm works is that in each iteration, you first take one of your boxes, you branch it, which means divide into 2 halves. Then you try to reduce the size of each one of them by removing parts where you know that the optimal solution can't be. And then you update your bounds on the optimal solution by making a line search within one of your boxes. I will now show you a video of how it works. So you can see now how the box is divided into multiple boxes, and in every iteration some of the boxes are divided and sometimes they are removed, and after just a few iterations here you can see how you are having more and more boxes, but they are smaller and smaller and they are closer and closer to your global optimal value here. And they're essentially becoming like a small line area around that optimal point. In summary, we need to select a utility function in order to solve a resource allocation problem, and all utility functions are subjective. So the pragmatic approach would be to select one that enables efficient optimization. A good choice then is any problem with polynomial complexity, such as a weighted maximum fairness problem, where we can select the weights in order to adapt to other needs that you might have as a system designer. By contrast, the bad choice is the weighted sum performance problem, because it's generally NP-hard and has exponential complexity in the number of users, because this is the number of dimensions in which you need to create these boxes that you are branching in the BRB algorithm. And you could solve it with 2 users. I showed you a video of that. 4, 5, 6 users might also be solvable, but then it becomes really computationally heavy. So you should avoid this, even if it's sometimes needed in order to solve some virtual queuing problems in practice. What I have shown you now is a complexity analysis for resource allocation with any dynamic operation clusters. So the same optimization algorithms can be utilized with ideal joint transmission, with coordinated beamforming, with cognitive radio, and sometimes you might have some extra characteristics that simplify the problems a bit, but in general, this is the kind of complexity you should expect. if you have multiple antennas, which is the main point here, you have higher computation complexity, but also higher performance for your users. There are some structural insights into optimal beamforming that can be extracted by solving the optimization problem that we considered previously. So in general, we have kr times n complex valued optimization variables. So it is these beamforming vectors v1 to vkr. So they are kr of them and they have n entries each. But this can be reduced to kr positive parameters, one per user, when we have only one total power constraint. So what one can show is that any resource allocation problem is solved by beamforming vectors that have a particular structure. We have a power scaling factor here. We have the channel vector to this user, and then we have an inverse that contains an identity matrix and a summation of all of the different users. In the sum, we have the channel to that user times itself. We have a lambda I parameter that we need to select, and we have the noise variance. And inside here, we could also have the C and D matrices, but for brevity, we have turned them into identity matrices. And the thing we need to select is the priority for user k, which is this lambda k parameter. And this is basically the Lagrange multipliers from this easy problem if you are solving them at the optimum to your more complicated resource allocation problem. And this structure can be illustrated geometrically like this, that we are having one particular direction in which we would be maximizing the power to our desired user. So if we beamform in that direction, along the channel to this user, we maximize the channel gain. We have a subspace spanned by the channels to all of the other users. And if we beamform orthogonal to that one, we will have no interference between the different users. And then the optimal choice, which we have with our structure before, will be somewhere in between these different extremes. And this priority lambda case will determine where we are. You have some kind of selfishness versus altruism trade-off here, where the selfish thing would be to beamform so that you maximize your own received power, and the altruistic thing would be to minimize interference that you cause to other users. And when we are now considering this kind of parameterization with only one parameter per user, it might seem like we have reduced the computational complexity of solving some kind of spatial resource allocation problem. But if we have an original problem that is hard to solve, well, searching through this kind of smaller size parameterization is actually not reducing the complexity category. So if you have a hard problem, you still have a hard problem. But what people have been discovering over the years is that if you select these priority parameters in a heuristic way, it performs remarkably well. So there are many examples starting from 1995 where people were proposing things like the transmit Wiener filter, regularized zero forcing, signals to liquid beamforming, virtual SINR beamforming, and so on, which were all based on the concept of using this optimal structure and setting the priority parameters, for example, equal for all of your users. And you can read more about this in this paper in the Signal Processing magazine from 2014. So finally we are coming to the summary. We have been considering multi-cell, multi-antenna resource allocation problem where we would like to divide the power between users and spatial directions when we're optimizing the performance to solve a multi-objective optimization problem. And for such problems, the Pareto boundary is the set of all the efficient solutions that one might consider. But we only need one solution, so we need to select the subjective utility function. And the selection has a fundamental impact on the solvability, how complex the solution would be. And with multi-antenna transmission, we have more possibilities, but also higher computational complexity, but it doesn't change the complexity category to a large extent. The pragmatic approach would be to select the utility function that enables an efficient optimization solution. And polynomial complexity is achieved by weight at maximum fairness, where you can tweak the weights in order to get the performance that you want as a system designer. A bad choice is the weighted sum performance metric, which leads to optimization problems that are not solvable in practice, at least not optimally. Finally, we could also consider the parameterization of optimal beamforming and select its coefficient in a heuristic way to get decent beamforming solutions as well, if we don't want to solve the entire optimization problem. The main reference for this lecture is our book, Optimal Resource Allocation in Coordinated Multi-Cell Systems. So here we are providing a thorough resource allocation framework with more parameterization, more structural insights, some guidelines for scheduling and how to form these dynamic operation clusters in practice. We have distributed MATLAB code for all of the algorithms, and in this video I described you how to solve the sum performance problem, the maximal fairness problem, and this easy problem in general scenarios. In the book, we're also considering a larger set of problems with some other metrics and also conditions such as using zero forcing and single antenna transmitters, where we can change a little bit what problems are solvable easily or not. Finally, we have some further extension in the book to imperfect channel knowledge, to distributed implementation of our optimization algorithms. We consider multicasting, multi-carrier transmission, and multi-antenna users as well. So there is a gold mine of things to learn by downloading our book and read it. Thank you for watching this video lecture all the way to the end.